Any questions till now? Yep. So we proved this theorem, Riemann's theorem, which basically says that this L minus D difference is has a threshold as you go to bigger and bigger divisors. So here you are just doing x to the m. So this is a very simple divisor because x, the pole of x is basically a single point, and when you are increasing m, you are just increasing its multiplicity. So what this is saying is actually something even stronger. It is saying that you just pick a point on your curve and just keep increasing the multiplicity, and that already L minus D difference will give you a threshold, and that threshold is what we define as genus. Now this is a bit different from what Riemann did, because Riemann actually proved this as a theorem connecting L sheaf with the geometric genus, right? So for him it was a property, but for us it becomes a definition. So if you are interested, you should read the complex analytic proof where genus is already well defined as wholes, and then you see why these two things will be equal in that word. But in our word it won't be important, because we just take this as a definition of the number being called genus, and it's independent of x. So that's the second part we have shown.
So you're saying that it's like taking multiplicity and
Yeah.
taking like how can we interpret an L minus D like?
Yeah. So how can you the best way or the simplest way to see this is for the projective line. I don't think there is anything simpler than that. So what is for the projective line, which means the function field is kx. So for k bar x, what is the genus, right? For what is the genus for the project? So the C is just P1. What is the genus of the curve in this case? So you can take a point P and so what is LP? So how many independent functions can you write down over the line? So function will just be a univariate, right? And without the homogenizing variable is simply a univariate. It should so either you can look at the constant functions, so that's one type of functions that's always there. So in fact we should always consider LP minus 1, because constants are there. Other than constants, what the functions f they have to satisfy f should have a pole at P of multiplicity 1 and not any worse, right? So if P is your point alpha, you just look at 1 over x minus alpha. That function has a pole at alpha. So that is just one kind of function. So this is equal to 1. LP is equal to 2. Right, and what is the degree of the point? It's just 1 for algebraically closed field. So you see that the difference LP minus 1 degree is equal to 0, and that's the genus.
So can you repeat argument LP minus 1 is equal to 1?
Yeah, so for that you have to look at the sheaf. So the functions, so this will be a K vector space. So clearly constant functions will be in the LP sheaf, and also yeah, let's take P to be the point alpha. So you'd look at the function 1 over x minus alpha, right? So 1 over x minus alpha, principal divisor is what? Its pole is the point P, because x equal to 0 it becomes infinity, but it also should have a 0, right? Every function has zeros and poles. So what is the 0? The what? Sorry, this is minus P. What is the 0? That's infinity. So it's infinity minus P. So clearly this is greater than equal to minus P. So 1 over x minus alpha is an LP by definition, because you want functions such that f plus p should be greater than equal to 0. That is being satisfied. And yeah, over the line you don't have any other option, right? That's all.
What if you try and give more zeros? Like if you write down x minus beta over.
Then multiplicity will increase of the pole. Yeah, so then what will happen is minus p will become minus 2p. Then those functions will not be in LP, because you are only interested in functions whose poles are not any worse than minus p.
No, the pole will still be order 1 over it.
No, but when you give more zeros, you have to give more poles.
You give pole somewhere else at infinity.
Yeah, but that is not allowed. Nope, none of the poles should be other than minus p. So that is the difference between this restricted LD sheaf and the whole LD sheaf, right? Because in this is the whole LP sheaf. So here you have to actually go over all the points on the projective line. You have to compare with everything. So none of them should be pole except P, or there is no pole, in which case it's a constant function. So this is what I was saying, that LP minus 1 is just this interesting function 1 over x minus alpha, and any linear combination of these will work also. So you get LP minus 1 is equal to 1, which is also the degree. So you get the best. Actually in this case, yeah, you get this equality 0. But this is not enough to complete the genus calculation, because you have to also look at higher multiplicities. So you also have to calculate LMP minus 1. What is this? And it is here that you have to see that this will be equal to m, while the degree is equal to m also.
The function we want as x by alpha and x by alpha square.
It's actually true for all m, yeah, which then means that genus is 0. That calculation I am skipping because it's the same calculation. Okay, so that is why the projective line has genus 0, because even if you keep increasing the multiplicity of this point, which is you are increasing the degree of the divisor, linearly the L functions are also increasing. The LMP sheaf is also growing, and you can already see why. It's just 1 over x minus alpha, and the other will be, the new thing will be, 1 over x minus alpha is square, and the other thing will be, that's the third thing actually. So you have 1 over x minus alpha, and you have 1 over x minus alpha whole square. That's the basis. So hopefully this answers your question.
So
Right.
basically, like degree shows that there is some connection between the poles and the Galois representation.
Yeah, but without jumping to bigger objects, it's actually telling you something much simpler. It is just saying that uh, in your favorite curve, is this property satisfied, what was being satisfied for the projective line, that wherever you want you can put a pole, and as you increase the multiplicity of the pole, proportionately or linearly the functions also should grow. So how far is your curve from this property? So as the curves grow more complicated, you will see a loss, and those are the holes. So yeah, so intuitively it gives you this idea of genus versus holes, but now purely algebraically. So you don't need to see or define any loops or holes. You can just measure it by the LMP. Okay. So what we will do next is, as promised, we will now do Gustav Roch's extension of Riemann's theorem. Okay. Which is to explain this degree of speciality, right? For every divisor D, what is a good interpretation of delta D, which is the why is it that LD minus 1 minus degree plus G is not 0? Why is it positive? So what is the explanation for that? So we now prove Roch's theorem. So this will require several lectures, but just to anchor you, here is the theorem. So Riemann-Roch theorem says that there exists something called a canonical divisor. W, such that for all the divisors delta D is equal to L of W minus D. Okay. So this is pretty nice because as the name suggests, you have been able to identify this global or canonical divisor W, which will work for every divisor D. So delta D is actually another, it's again L sheaf of some other divisor, but you have a minus there, so you have minus D here. So it's kind of a dual of LD sheaf. So it's I mean, in more advanced algebraic geometry, this result is seen as a duality theorem. It's probably called Serre's duality theorem. But we will not do Serre, we will just do Roch, because you will see that even this is not, this will require some abstraction. So the idea of this is, the proof is, this W minus D is kind of a dual of D. So for example, can we realize it as linear maps from K mod LD to the base field? Okay, so duality means that instead of this vector space LD, you should look at functions which vanish on the LD sheaf, right? Because you are interested in kind of minus D. So, I mean, the very vague idea is that you should look at these maps. So these are the linear maps which annihilate functions in LD, but not others, right? So K mod LD is the subspace, and dual of it is basically linear maps which evaluate a function to a field value which is the base field small k. So we want to realize delta D as this object, and yeah, we'll try to achieve that. We'll not be able to achieve that exactly, but we'll kind of follow this template.
Because that thing looks infinite dimensional, right?
Yeah. So that is one problem. This, if you go over all the small k vector space of all the functions, that will be even modulo LD will be infinite dimensional. So that won't be good for our computational algorithms. You have to somehow replace it by a finite object and then look at home of that to small k, homomorphisms to small k. Yeah, and then finally that thing has to be exactly equal to delta D. That's the goal. So for that, something completely new and mysterious is needed, and yeah, so that will be the following. So we'll achieve this via by moving to more abstract functions than the function field, and we'll call those things Adeles. Okay. So this is also called répartition. This was the name given by Chevalier. But we'll continue to call it Adele. In some algebra literature, it is called pre-Adele, but I don't think it will matter to you because you haven't seen any of these things anyways. So I'll just call it Adele. So this will be, I mean, every function is an Adele, but Adeles will be more complicated looking. Okay. Which is why I'm calling it more abstract than the function field. So what is this? So let's directly give the definition, because definition is not very hard. It's just that it's not clear why this thing will be useful. So for curve C, again smooth projective curve given by a transcendence degree 1 function field, a tuple R of rational functions is called an Adele. I leave the accent. So it is called an Adele if the valuation of all these coordinates, functions in the coordinates, is non-negative except for finitely many.
when you say P in C, now you mean it as a maximal ideal or as a...
Yeah, those things are equivalent. The old remark continues everywhere. If you are in a finite field, small k is a finite field, then you have to talk about P as a cloud of points or a prime ideal. If you are in FP bar, algebraically closed field, small k, then you can work with actual points. So, yeah, so it is an infinite tuple first of all, which is the problem. I mean, which is the which is a bit strange. So for every point, you are basically assigning a rational function in a syntactic way. The only constraint is that except for finitely many points, everywhere else the valuation at that stock should be non-negative. Okay, so for finitely many places, P valuation could be negative, which means that the function that you have put at that place. So think of this as like these are infinitely many points. You can even take the projective line. So on every point you put a function and you make sure that only in finitely many places the functions you have put actually have those poles. Everywhere else it has to be non-poles.
Definition more very much like the rational maps, because there also be the certain poles we wanted to certain points.
Oh, rational map that we defined. No. It's no. So this will be completely different from whatever we have seen till now.
So there also is the idea like certain places we can't define the function as well.
Yeah, but see, so it is important to realize that this is very different because there is no global rational function which comes even close to this. Because the places where valuation of RP is non-negative, you essentially can put very different functions for point P1 and for point P2. So it will be impossible to actually see what is there a function in the function field which is close to this. So this R can be very, very different from whatever function you look in the function field.
Building this from multiple rational functions, that's very complicated.
Yeah, because it's actually a tuple of infinitely many rational functions, and this is truly infinitely many.
So this does not have a concept of continuity or something, right? I think.
Well, anyways, continuity, we only talk about Zariski topology, so you can define continuity there, but I won't, so it won't be needed. But yeah, the topological definitions, then you have to refer to Zariski topology. If you force it, it will not be very different from what you have already defined for RP. RP is a rational function, so you can, and it is defined at that point. Yeah, but you don't know how it behaves on other points, and you cannot definitely compare between the function you put at P1 and the function you put at P2. So they can be completely independent, and this you are doing infinitely many ways. So that's an Adele.
But what's the reason with requiring this valuation negative except for finitely many?
Yeah, right. So that is true for functions. Functions in the function field. If this small r, you just pick a function from the function field, say y or x, then you know that it can be negative only at finitely many points, right? Because negative means that you are talking about poles. Now you already know that for rational functions, poles are only finitely many. We have shown this in the first month, right? So both poles and zeros are finitely many. So this is just taking that property of functions, which is why functions are contained in an Adele. Every function is an Adele element, or an Adele actually. Yeah, every function is an Adele, but Adele may be very, very far away from a function. So RP is, well, obviously called the pth component of the Adele R. And the set of all Adeles will be fancy A. And 0, the tuple 0, that also fits in, right? Why do I want to say that separately? I think it's already included. Anyway, so the set of all Adeles is, we'll call that this A for the curve. Yeah, so the definition is simply, I mean, it is just at this point it is just algebraic or even syntactic. You don't understand why this will actually help. So let's now prove some properties. So proposition 1, yeah, from two propositions it will be clear that this object is necessary for what we want to do. So proposition 1 shows that there exists an embedding of functions into Adele. So functions are Adeles. A is a K algebra, but it's not a field, right? So here already you see that the function field was a field, but Adele is now not a field, but it contains the function field as a subset. Valuations can be defined on Adeles. So for all point, valuation extends from K to Adele. So we know what a valuation is with respect to a point P on functions. The same thing we can actually extend in a nice way to Adele also. And fourth is the analog of LD sheaf. Is called AD. Okay, so this is a definition, and it also will be a well defined object. So by analog I mean just like you said that, see, once you have the valuation from property 3, now you can do the same thing which you did to define LD sheaf, which is there you said that all the functions f such that f plus d is greater than or equal to 0. You can now say the same thing, all the Adeles R such that R plus D is greater than or equal to 0. And what does greater than or equal to 0 mean? Compare every valuation for every VP, right? So AD sheaf is actually what we are looking for. This is why we defined Adeles. So AD sheaf will have much better properties than LD. So you remember LD, when we were looking at the dimension of LD prime over LD, we did not get an equality, we only got an upper bound. So for Adele AD we will actually get a equality. So it's you can think of this as a way Roch corrected the issues with LD sheaf. Yeah, any questions about these propositions? So I hope that the proofs will be very simple for you. Some of them you can already see, but let's just go through them to warm you up with the Adeles. So how do you show? So what is this embedding?
Same function as
Yeah, the same function you put in every coordinate. And call that tuple R. So this will just be x for every coordinate p in C. So this will be the pth coordinate of R. And this is fine because you know about functions that it has finitely many poles and also finitely many zeros, but you only want the first half. So finitely many poles condition is satisfied. Everywhere else, the valuation is non-negative. So in fact, we know that the valuation of x is 0 except for finitely many points on the curve. So you actually know a stronger property. So everywhere you will see 0 except in finitely many places where it's positive or negative. So that means it's an Adele. So we will abuse the notation. So from now on, we'll use x and r interchangeably. For functions.
It means you use only x.
Correct. So I mean, when I want to talk about Adel as coordinates, I will have this infinite tuple everywhere x. When I want to do not go into those coordinates, I can simply say that x function x is an Adel. Okay, there is obviously there is a difference because x is a single element, while tuple has infinitely many coordinates. But with this understanding or this embedding, there shouldn't be any confusion. So I'll just use x as an Adel also. Okay, second property is about K algebra. That's also is easy. So I have to show you how to add and multiply. So let R be RPs and R prime be RP primes. These are Adeles. So how do you add R and R prime? Well, coordinate wise. There is nothing else that you could have done. You have infinite coordinates, so you can simply just add coordinate wise. Why is it an Adele again? Because when you look at the valuation, how many times can it be negative? And let's also define in the same way R prime. And let's check whether these things are Adele. So valuation of RP plus RP prime negative means what?
Minimum of there has to be negative and there has to be finitely ones also.
No, if it is negative, then it means one of them is negative. Yeah. but the possibility for that in RPs and in R prime P's is only finite. So it's only the Cartesian product of the finite locations. Everywhere else you will see non-negative. So that's done. So this means that RP plus RP prime is an Adele. Sorry, R plus R prime is an Adele. And what about valuation of RP times RP prime being negative? This again, since it's a sum, one has to be negative. Same thing. So this again means that the product is an Adele. Right. So we have shown till now three things. One is that the function field is embedded. So in particular, the base field small k is also embedded, and you have addition and product. So you get a big K algebra. Okay, it's an algebra over the function field. Okay, third property, how to extend valuation. So valuation should send an Adele to integers. How will it do it? So on R, it should do what? Yeah, I mean, you just look at the pth coordinate, you forget about the rest. And show, you can just check that VP satisfies valuation axioms. Okay, because you can check it on addition and product, and it will just inherit the properties from the single function RP from that just pth location. So that becomes a valuation. So you have kind of this metric now on Adeles, just like you had on functions. And with this you have now the AD sheaf. So let D be a divisor, which is just a sum of points, formal sum of points on the curve. So you can just define AD to be those Adeles such that for all the points on the curve you want the valuation on that Adele to be greater than equal to minus order of P in D. Right, so same syntactically the same thing that you did with LD sheaf. And the same way that you can add elements in an LD sheaf, you can also add elements here, right? So R plus R prime, both R and R prime being in AD sheaf, you can see that the sum is also there. Because each of these inequalities that you are talking about, this is only for a single valuation, which boils down to just the pth location. So the sum will also satisfy because the sum is coordinate wise. So you get that AD is a small k vector space. Right, so that gives you all the properties you wanted. Right? Okay. So now we'll get more interesting things once you are warmed up with Adele. So the first property is that Adele R has an associated positive divisor dr. Just like every function has a divisor, is it the same thing? No, so I think I should define this, what I mean by this. So what I want to show is that R contained in EDR. That's what I mean. Every Adele R is contained in some ED sheaf for some divisor D. So what was this for functions? If I take a function f, then it is contained in which LD? Yeah, it was this. I think the infinity part, f infinity or f0. Yes. So that's the thing. You basically want f plus d to be greater than or equal to 0, which means that the negative part, which is the poles, that f infinity part you should add, so that you get a positive divisor. So in the exact same way, the same proof will actually give you also dr. It's the infinity part of the Adele. But we'll prove that. For divisors d prime greater than or equal to d, again we will look at AD prime mod AD, which is a vector space and the dimension of it over the small k field. So this was, we showed an upper bound for LD prime over mod LD, right? What was the upper bound? Degree difference. So the amazing thing is that now with Adele this will be an equality. Okay, so you can already see the signs of where we are headed. Since this has become an equality, so the losses which we were incurring in Riemann's theorem, we will be able to analyze that, because this equality will kind of give you other equalities.
The A of D itself is not finite, unlike L of D.
Wait, what? L of D also in the beginning a priori was not finite dimensional. That we have to prove.
Here,
So we actually first prove this dimension upper bound, and from that we deduce that LD is finite.
for AD,
And now for AD maybe you can do the same. You look at degree D equal to 0 and you see. So what is A0? So you will want A of 0 will be those R's such that in every coordinate you have valuation greater than or equal to 0.
yeah, it's not right. You can have just a constant.
You can just have different constants in different tuples here. Yeah, that's interesting. So A0 itself is actually infinite dimensional. Okay, that's true. Still, so it's actually very mysterious then that the dimension of the quotient is finite. Yeah, we'll prove this, and finally the reason why we defined all this is that the dimension of AD, sorry, A mod AD plus K. So what is this? A is the whole Adele algebra. AD are the, I mean this based on the divisor, the sheaf, AD sheaf. That's a small k vector space, and big K is also a small k vector space, so we can add them. That's again a vector space, and we are looking at A vector space mod this. Both of them are infinite vector spaces, but the dimension of this quotient vector space is delta D.
This was a direct sum, right?
Why is it a direct sum? We don't know that, right? Because big D divisor is arbitrary, so it usually will not be a direct sum actually.
Will be,
Usually it won't be, right?
usually it will be, right? Because if your A of D contains constants, then your D should be.
No, but AD will contain functions. So already there is an overlap. AD has functions, let's say, because it in particular it has LD. So LD is a bunch of functions that is shared with K.
That's a capital K.
Capital K, yeah. No, small k is already there. That's capital K. So usually it is not a direct sum. There is a huge overlap. In particular, as I said, LD is an overlap. But when you mod out Adeles by this, you get the degree of speciality of the divisor D. Okay, so we have characterized already, and this won't be very hard. We can finish the proof right here. So already you see that this A mod AD plus K is the dual object of LD. This is the dual. It comes from Adele. So, and actually the technical reason is property 2. The property 2 is an equality, so it actually gives us a better handle. But you will see. So first I think we already saw. So just define dr to be kind of these poles like you did for functions f infinity. So here what you will do is minus valuation r sum over that for those points where valuation is negative. That's the sum. Now it's a divisor. As it's a finite sum. So it's a divisor, and you can talk about ADR. So when you look at ADR, clearly R is contained. Because when you do the sum R plus dr, yeah, you will see that at every point the valuation is non-negative. So this is like f infinity. That's the associated, that is the meaning of associated divisor. It's like we could also call it R infinity actually. Right, so more interesting thing is the equality property. Let's do that next. So as before, S will be the support of D prime and D. it suffices to show that this we had already studied restricted LD sheaf, right? We had already shown when we did LD sheaf that this restriction uh, quotient of the restricted LD sheaves has dimension, difference of the degrees. So all we have to show is that this is actually isomorphic to AD prime mod AD. Right? Is this clear? So by the quotient of LD restricted result will be done. So I'll just construct this isomorphism. So this you can actually see as the place where Roch might have gotten the idea of looking beyond functions. Okay, that's basically you want an object which is slightly bigger, in fact infinite dimensional, but in the quotient you get it equal to the isomorphic to the restricted LD sheaf.
Rock essentially invented cohomology.
True, but cohomology word was not there. Yeah, since dimension of left hand side is degree difference. So we have to start with the LDS. Already LDS, what is the map to AD? Let's do that. So a function x should be mapped to Rx, which will be slightly different from what you expect. It's not that every coordinate will put x. So where Rxp is defined like this. So you put x if p is in the support, else 0. Okay, so this will be the correct map from the restricted LD sheaf to AD. You only put x in the places coming from S, other places you put 0. So this phi is clearly a k linear map of vector spaces. You add two things, x plus x prime, and you can see that it respects the image. That you can see it simply by coordinate, looking at the action on the coordinates. And right, so LDS is basically the modulus, right? So LDS is going to AD, so 0 is going to 0. So hence we can now extend phi to the quotient subspace. So phi extends to an injection. From LD prime sub S mod LDS to AD prime mod AD. claim is that this is onto as well. Wait, is it clear that this is a injective homomorphism? So if phi sends an function f to 0, which means that its image is in AD, right? Yeah, so then in the interesting places, you only focus on these finitely many interesting places. There you are saying that it's 0. So which means that it's 0 in LD prime as well. LD prime S in LD prime S. So injection is actually easy. Why is it onto? That is the tricky part, because previously we only had an upper bound. We did not know whether it actually reaches the upper bound. So this is the hard part. Why is phi onto? So we have to show that every element on the RHS has a pre-image. So let's take an element. Let R be in AD prime. It's an Adele. So by the approximation theorem of functions that we saw in the early on in the first month or second month, there exists a function such that u minus Rp for all p in S. So note that S is a finite set, so we just look at those points and we want the valuation of, so we want u minus Rp to have, in a way approximating these poles that D is giving you. So on the point is that R is an Adele, but it has it has infinitely many coordinates, but if we only focus on these finitely many coordinates coming from S, we want to only approximate that part by a function u, okay, up to the orders provided in D. So that will give us a function u by the approximation theorem. And let's now see whether this u is a good preimage. We'll show that it is. That would finish the proof. So let's just check the valuation of this function. So VPU is what? It's the minimum of u minus Rp and Rp. What is valuation of u minus Rp? This is at least minus order of P in D, and what is valuation of Rp? So by the assumption that R is in AD prime, right? That also lower bound minus order D prime. Which gives you D prime was greater than or equal to D, so yeah. So this means that, so this is true for all P in S. So which means that U is a function in LD prime S. So that is what approximation theorem has given me. So it's a good pre-image. We just take this as a pre-image, and let's look at its image. I mean, we have to check the image basically. So consider let's call it RU. It's a function, so phi sends it to an Adele, RU is the Adele. Yeah, all that is left to check is it R? Is RU R? We'll show that RU may not be R, but the difference is in AD. So with that we'll be done. Right, so we just have to show that RU is actually R mod AD prime, mod AD, because in the image you only want to be correct up to mod AD. So let's do that. So yeah, so go over the valuations. Which is, what is the valuation of RU? It's basically the so it's basically valuation of U, right? Because at P it looks like U, so U minus R. And in fact in R you just look at the pth coordinate, this. Yeah, look at the pth coordinate, so that's RU at P is just U and R at P is RP. And that we have already established by construction, we have this. So for P in S by construction we have this. This is not surprising. What will be surprising, or what you have to carefully analyze, is all the other points, because now you are in Adele world, so Adele world has infinitely many points. What is happening in S complement? In the curve minus S, what is the valuation? Okay. So RU at those points we have defined via phi to be 0. We put 0 there. So 0 minus RP. So what is valuation of RP? This we what is VP RP? That is by the definition. Yeah, so R came from AD prime. So you get D prime. Right? So there is a difference. These good points, on good points the valuation is by minus order D. On the bad points it is minus order D prime. But anyways, the bigger one of them is minus order D, so you get that. So this means that for all the points on the curve, RU minus R is greater than or equal to minus, wait, D prime was greater than equal to D. No, will this be enough? Wait. No. So there is something I missed. What is this order of D prime at P? What is this? See, P is outside S, right? So it is outside the support of D prime. So it's actually 0. So in all cases, it is at least order of D, which means that Ru minus R is in fact in AD. Right, that's it. So this means that phi is onto. So phi is an injection and it is surjective. So that makes these two isomorphic, which means that we have the degree equality. Yeah, any questions? Yeah, so once you have seen the proof, now the idea is you can go back and see that the idea is pretty simple. It was just you took an Adele from AD prime and in those finitely many places you approximated a function u and put that. So basically from an Adele you are able to get a approximate function, and once you have an approximate function you use that in LD prime S and just finish the calculation. That gives you an isomorphism. Yeah, so although left hand side you had restricted LD sheaf, on the right hand side there is no restriction, it's actual AD sheaf. This is why this Adele was created, to go out of this support restriction. Okay, so with that we can prove property 3 also. I think we won't be able to finish it today. Let's just do 50% of that. Yeah, so property 3. So let us show that the dimension of this A mod AD plus K is at most delta D. Okay, this is what we will show, and next time we will show that it's at least delta D. So suppose there exist each elements, each Adeles R1 to RH in A, which are K linearly independent mod AD plus K. Yeah, and for this basis we will work out some calculations which will imply that H has to be less than equal to delta D. Okay, so let's do that. So by 1 get the associated divisors. get divisors dr1 to drh all positive, such that for all these Ri is in A dRi. So these are kind of the Ri infinity divisors. And we can take the LCM of these divisors. So LCM will be basically you look at the points which are appearing in these divisors and pick the maximum order, right? So D prime is kind of a upper bound on all these positive divisors. So D prime is the biggest amongst which is bigger than all these, and we'll now work with AD prime. So in particular, this means that Ri is in AD prime. This is the common one. So we just took the common one, and this actually now helps us in deducing that R1 to RH is a basis of AD prime mod AD plus K. I mean, we started with a basis. So since it was a basis before, with AD prime also it's a basis. And now we have this this quotient space, right? So we have a basis of size h of AD prime plus K mod AD plus K. Is that clear? So it's only some pre-processing. We haven't really done anything great. What we have to now do is we have to actually calculate the dimension of this and show that it is somehow related to the degree of speciality. So here is the calculation at the level of subspace. So AD prime plus K, let me ignore the bracket. So this quotient subspace is isomorphic to this. Actually, bracket somehow will be necessary. Let's continue with that. So the first is this, I mean, it is simply a property of vector spaces. So you have V mod U. So what I am saying is I can do V mod V intersection U. So you can prove this by just pick a basis of AD plus K, the modulus, and extend it to the bigger basis, and then what? So this actually just is extend the basis of the denominator to the numerator. Do you see that will prove this? I mean, this isn't a property to do with Adeles, it is just a property of vector spaces. This V mod U you are writing as, or to be precise, U plus V mod U is isomorphic to V mod V intersection U. It is just this that we are using. Well, because of this basis argument, you can see that the dimension of left hand side vector space is the same as the RHS space, right? Because it's the, so when you are extending the denominator basis to numerator, suppose you added R basis elements, that R is the dimension of both left hand side and RHS. Okay, so the dimensions are equal. That's one thing. Now, why is it an isomorphism? I mean, the isomorphism, you can just use the obvious thing. The vectors in U are considered 0. So, essentially in LHS, you only have to consider vectors in V, and that has an obvious image in the RHS, right? So using just basic linear algebra, you can see that the two vector spaces are isomorphic, even if they are infinite dimensional. Okay, you can turn this into a proof, and yeah, let's finish that next time, because such things I have to repeat.